Okay, this happy little guy here is a 74595 serial input, parallel output 8-bit shift register. It has two extra features, being there has an output enable, which is active low, and then we have output registers. So let's take a look at what's inside. First of all, it's an 8-bit shift register, so it's going to have 8 individual bits that can be worked with. So 1, 2, 3, 4, 5, 6, 7, and 8. Each of these bits here gets connected, or is shift register, so it's connected to a serial input called SER, and it has an associated clock pulse pin. So these are all the external pins I'm drawing out here. This is SR clock. So every time you pulse SR clock, which just means making it go high and then low, every time you pulse it, it's going to move whatever's in serial into the first bit, first register, and whatever was in the first register to begin with gets moved into the next one, and the next one, and the next one. I'm going to use colors to represent all of these actions here. So whenever SR clock, which is red, occurs, whenever the pulse occurs, whatever arrows are red are occurring as well. So serial, the data is taking it in, put it into the first one was moved to the second one, second one was moved to the third one, and they all occur at exactly the same time. Whatever was in the last register, if you don't have anything connected externally, there is a pin to connect it externally, but if you don't have anything there, it just ceases to exist. So it just falls out of the register, honestly, for all intents and purposes. Next, we have a output register. So this is also 8 bits. So we have all 8 bits here, and these are actually connected to the outside world through the output enable, but I'm going to use, let's say, blue to represent this. There is another external input pin called R clock. Whenever R clock is pulsed, meaning it goes from low to high to low again, everything that was in the shift register clock gets moved into it all at once in parallel. So you pulse in data, 8 bits would mean 8 different pulses going through all the shift register bits. And then once that's done, you pulse R clock once, loads everything into it. And now this is completely separate from this. The data is still in the shift register, but we don't care about it anymore because we've already copied it over to R clock, the register clock, or the register output register. And connected to that is the actual pins, the physical outside pins. And they're all labeled by letter, A, B, C, A through H. And for that to actually show up on the output, for the output register to show up on the output, we have a pin called output enable, which is active low. So if you pull this low, everything that was in the simple register shows up on the output. If you just leave it low, then whatever is on the register will always be on the output. And that's, for the most part, what everyone does. Unless you're sharing a bus in a processor or a system, output enable is usually just tied low and left low. All right. So to go over the process again, we put data on serial, clock it once, put another data on serial, clock it once, put another bit of data on serial and clock it once. So the first bit you put in is going to eventually show up here over 8 clock pulses. So let's say we do 0, 1, 0, 1, 1, 0, 1, 0. It could be anything, it's random. As soon as our clock is pulsed, whatever's in here moves up to the top. I'm going to use green for that. 0, 1, 1, 0, 1, 0. So now this shows up, and you could pulse SR clock as much as you want. It's not going to change whatever's in the output register. You could the processor in the background could be just running a new set of binary digits here, and it's not going to affect what's up here until it's ready with all 8 bits. If you wanted to see these in the pins on the output, you would bring output enable low, and in the upcoming lab, we're just going to have simple LEDs on here. LEDs and a resistor, which then goes to ground. So we'll be able to see whatever's on the outputs A through H through the LEDs. Now you might ask why this matters for an Arduino, which has a ton of pins and is completely configurable, but because of this part here, this little movement from the last bit to the outside world, you could have another 8-bit register on that. So you could have a 74595 next to a 74595, another one. And if you had, let's say 10 of them, that's 10 times 8 bits, that's 80 outputs. So you can control 80 outputs with the same exact 1, 2, 3, 4 lines. So 4 lines for 80 outputs, that's a pretty good expansion of the ability to control outputs.